Hello everyone. On this video we will be going over the squeeze theorem, which is also known as the sandwich theorem. Okay, and this is useful when you have really complicated trigonometric limits. Okay, so we'll go over the general idea first and then we'll throw a couple of examples in there. Okay, so let's say if you have three functions. Let's say we call one h of x, and that h of x is less than or equal to some function we'll call f of x. And that f of x is less than or equal to some function we'll call g of x. Okay, so in other words, f of x is between h of x and g of x. Okay, so if this is true for every x value, so for all x in an interval, I don't know why I'm thinking internal, containing a value that we will call c, except maybe at c itself. Okay, now also, let's say if the limit of h of x as x approaches c is equal to some value that we'll call L, and we know that the limit of g of x as x approaches c is equal to some value that we'll call L. Okay, so if each of the outside functions have a limit of L, then it's safe to say, move that up a little bit, the limit of f of x as x approaches c exists and is equal to L also. All right, so that's the general explanation. Now let's look at how it would look as far as a graph. All right, move that up a little bit. Okay, so let's say this is our x-axis. Okay, so let's say this is our value c. Okay, so let's say our h of x is some graph that we'll say is this. Okay, it could be any graph. We'll just make this our h of x. Okay, and let's say our g of x looks something like this. Okay, so what do we know? We know that the limit of h of x is equal to L as x approaches c, and the limit of g of x is equal to L as x approaches c. So as both of these approach c, which is about right here, their limit, L, and we'll just make L this straight line here. That's your limit. Okay, this one gets as close to the limit without passing it, and h of x gets close to the limit without passing it. Okay, so what does that say about f of x? Well, let's say f of x, let me move this so that looks more like an L. There we go. Let's say this limit here, or this function here, is your f of x. Let's say your f of x is some wild and crazy function that stays between g of x and h of x as it approaches c. Oh, I accidentally went under there. Did not want to do that. There, didn't want to actually pass by that h of x. Okay, so this odd looking function is your f of x. Okay, so what they're saying is, as you approach c, remember you're just approaching c, as long as for every value of x in the interval that you're looking at, it's below g of x and above h of x, then that function will have a limit that's also L. Okay, even though it may be a little hard to look at it and figure it out, you can do it by the sandwich theorem or squeeze theorem. All right, so now we're going to apply this to actual problems. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our examples. Let me move this down a little bit. There we go. All right, so let's say for our first example, we want to use the squeeze or the sandwich theorem. Both the same theorem, just different names sometimes, depending on where you look. To find, let's say for problem A, you want the limit of x times cosine of x as x approaches 0. And let's say for problem B, we want the limit of x squared sine 1 over x as x approaches 0. Okay, now know what you're thinking. Oh, just plug in 0 and that. Yes, you're plugging in 0 and that will give you the limit. But if the directions say use the squeeze or sandwich theorem to find the limit, didn't say use direct substitution. So that's the thing. You have to make sure that if the instructions say to use the squeeze or sandwich theorem, you want to be able to use the squeeze or sandwich theorem to actually find the limit, not just find the limit. All right. Now, before we even get started, there are two things you want to remember. First, you want to remember values of cosine of x and sine of x are always between -1 and 1. Okay, when using the squeeze slash sandwich theorem, you always want to remember this. Okay, and the reason why this is important, you will see in 1 second. Okay, so for A, since we have a cosine here, we know that cosine of x is between -1 and 1. Okay, if you drew a cosine function, you'll see it bounces between -1 and 1. Okay, but we're not looking for cosine of x, we're looking for x cosine of x. So what do? Multiply each section by x. All right, so once we do that, We multiply each one of these sections by x, so you have negative 1 times x, which is x. Well, negative x, sorry about that. Less than or equal to x cosine x. Less than or equal to x times 1 is just x. Okay, so what do we do now? We'll apply the limit to each section. As x approaches 0 to each section. Okay, so that means, give that a little more room there, move that up some. We have the limit of negative x as x approaches 0 is less than or equal to the limit of x cosine of x as x approaches 0 is less than or equal to the limit of x as x approaches 0. Okay, so all we did was take the limit of each section. Okay, now we're looking for the middle limit. Okay, that's our problem. Okay, well, why did I put less than here when I meant to put the, here we go, as x approaches 0. Okay, now here, you can just use direct substitution here, because the limit of negative x as x approaches 0 is just 0. So you have 0 less than or equal to the limit of x cosine x as x approaches 0. And on the outside, less than or equal to the limit of x as x approaches 0, just using the direct substitution, plug that in, is just 0. Okay, now if you see here, if the limit below it is 0 and the limit above it is 0, then sandwiched in between, that limit is also 0. Okay, so by the squeeze theorem, we'll squeeze slash sandwich theorem. The limit of x cosine of x as x approaches 0, move that up some, is equal to 0. Alright, so it's not super duper tricky, but it is helpful. Alright, so if you are still writing, feel free to press pause. But I'm going to do problem B on the next page. Alright, and we'll continue this one. So we'll do problem B, which is the limit of x squared sine 1 over x as x approaches 0. Okay, and again, we're going to use the squeeze slash sandwich theorem. Okay, so just like before, we know that sine 1 over x is always between -1 and 1. Alright, so what does that mean? That means that you have -1 is less than or equal to sine 1 over x is less than or equal to 1. Okay, so that's all fine and dandy for sine 1 over x, but we need the limit of x squared sine 1 over x. So what do? We multiply each section by x squared. Alright, so that gives us -1 times x squared is -x squared is less than or equal to x squared sine 1 over x is less than or equal to 1 times x squared, which is just x squared. Alright, now once we do that, we have our middle function is matching our limit function. So now we just apply the limit as x approaches 0 to each section. Alright, so that means the limit of negative x squared as x approaches 0 is less than or equal to the limit of x squared sine 1 over x as x approaches 0 is less than or equal to the limit of positive x squared as x approaches 0. And we kind of separate that a little. Okay, so once again, once you use direct substitution here, you just have the limit of negative x squared as x approaches 0 is 0. Less than or equal to the limit of x squared sine 1 over x as x approaches 0 is less than or equal to the limit of x squared as x approaches 0 is just 0. Okay, so once again, if your middle function is between two matching limits, then by the squeeze theorem, squeeze/sandwich theorem, the limit x squared sine 1 over x as x approaches 0 is equal to 0. Okay, not saying that each and every time you do this it will be 0, but the approach will be about the same. Okay, so as long as you know how to start by putting them between -1 and 1, your sine and cosines, you'll be okay. Alright, so hopefully this made sense, and I will see you on the next video.